Thanks everybody for coming in. Once again, my name is Nikita Ivanov. I'm the founder of Chief Technology Office company called GridGain Systems. Before we get started, as always, I just want to, it's always kind of great to see so many familiar faces, so many new faces. I was reminding that, a couple of years ago, about 3 or 4 years ago, Abe Kleinfeld and I, we kind of looked around and asked, do we have a conference for memory computing? And to our surprise, we discovered that there's not a single conference for memory computing specifically for this subject. And a few years back, we decided to set up this conference, and the rest of the history. And we now basically have conferences going twice a year, once in the Silicon Valley or in California, United States. And it's growing and growing. It's really gratifying to see familiar faces, new faces, and the conference is growing. So that's kind of a cool thing. So when the conference committee asked me to put a keynote, I thought about what could be a good subject. And I'm usually not big on kind of prediction and kind of future talking, but I thought this topic, future memory computing, in our rapidly changing world, will be kind of an interesting topic because I've been in this business for almost 20 years, and I've seen this technology evolve. I've seen companies and products come and go, advance, change. And obviously, we don't know which in every product will be in the next 5 to 10 years, but I think I have a pretty good idea. What are the drivers? What are the pushing points for this technology? What will actually affect the products and technology in this space in the next 5 to 10 years? Those are fairly interesting topics, and we'll basically talk about them today. Before we get to it, it's always nice to look back at the history and kind of set the context for conversation. As a matter of fact, that was almost my second choice for the whole presentation, but I need a lot more time to talk about in memory. One of those days I'll have the whole talk about the history in memory computing. It's actually a very fascinating topic. But the caching, the in-memory computing or caching, the terminology of caching has been with us since literally the beginning. If you go back to literature and the papers, you can trace it back to literally late 50s and 60s. But from my point of view, we really have to look at late 70s, mid 80s, when the terminology like caching has really become kind of household name in the computer science. And the idea is very simple, as you guys all know, right? We can store some of the data in memory that otherwise would have to be fetched from a disk. And back in the 70s and 80s, disks were extremely slow. We were literally working with tapes most of the time too. So that was kind of no idea. And back in those days, the caching was just caching. If you guys can, launch the hash map in any programming languages, that's the extent of it back in those days. It was literally just a way to store something in RAM versus something on a block level device like tape or disk. Fast forward to the mid-90s and, I would say beginning of 90s, middle of 90s, the idea came around that instead of storing everything in one computer localized, why don't we string together multiple computers and try to use RAM of those multiple computers together. And that's basically the birth of distributed caching. And essentially, in many shapes and forms, that still exists today to a certain degree. But mid-90s, early 2000s is when this whole idea kind of were percolating and developing. And mid-2000s, and basically up until just a few years back, there was an era of what we called in-memory data grids or memory databases. As a matter of fact, the term in-memory computing really got, real recognition at about the same time. If you look back, and you probably can use Google for that, if you Google it, you start to hear memory computing first appearing somewhere, in the early 2000s. Just before that, it was always caching and caching and caching. And what has really changed, why we introduced the new in-memory computing terminology, is because the in-memory data grids, as we know them today, really added the whole slew of functionality to what we historically, named, used, or knew as the caching. Right, you have the transactions, variety of different query languages, key value SQL, or variety of different SQL. We also grew in the capacity. In the 80s, we were dealing with kilobytes and maybe megabytes. Data grids deal with now terabytes. And really, the last frontier, if you will, or maybe last iteration of a memory computing is what we call today a memory computing platform. That's again a cumulative change, a qualitative change, when we add a lot more functionality towards based on the memory computing. or developed in memory computing. You have machine learning in place. You have streaming analytics, a lot of different, massively parallel processing capabilities that were added to this kind of fold. It's also very interesting that about the time when memory data grids, about 10, 15 years ago, the memory computing really has changed from just the idea of keeping something in RAM to really a dual purpose. Today, memory computing is 50-50 split between in-memory storage and the parallel processing. In today's world, you won't find any in-memory processing system that doesn't have both. As a matter of fact, many would argue that today, in-memory computing is less about memory because most of the series in-memory projects have a persistent storage, but more about the parallel processing. That's a very interesting transition of technology. So anyways, what I want to talk today about with this context and this background, I want to talk about these 4 driving forces, in my opinion, 4 a kind of key changes or key development that will actually drive the adoption or drive the development of memory computing in the next 5 to 10 years. We'll talk about each of them individually, but new memory products. You guys must have heard about Intel Optane. You've heard about non-volatile RAM, different types of RAM. This is the hardware side that will drive our further adoption, further development of memory computing systems. HTAP. Sometimes it's basically hybrid transactional analytical processing. It's a combination of analytical and transactional processing in one system. We call it HTAP, we call it HOPE, we call it transanalytical processing. There's plenty of terminology here to go around. But this is one of the business use cases that will undoubtedly be almost #1 driver for the adoption of memory computing, because memory computing is the only, basically, is the technology enablement for this drive. We'll talk about it later. Cloud-native architectures. This actually is so important for memory computing today. In memory computing, one of the last technologies to get on a real cloud adoption with the real cloud-native architectures. And one of my personal pet peeves, complexity or simplicity. The memory computer today is probably one of the most complex pieces of software any engineer can use. And for this to grow and for this to really, increase in adoption, it has to change. And that's actually we're seeing across the board, across, our own products, and products we see in the competitor space. It's changing. We're working on simplification of that. Let's talk about our memory, the first one. There's a lot happening. We've been actually working with, along the science SNEER and, monitoring SNEER and monitoring development of a NVRAM, non-volatile RAM, for quite some time. For many of us, it's been a pretty slow process, but it's inevitable. If you look at the development of Intel Optane, it's one of the first, literally the last 30, 40 years, new silicon technology when it comes to RAM. And it's really going to be a transformational for us. What's really important to understand that none of the change will come quick. Any of these changes will actually be fairly slow and glacier in pace. Because think about it, with a new type of RAM, not only have to provide a hardware component, you have to actually produce that and make it economical for people to buy, make it available in the clouds. You have to change the BIOS chipsets. You have to change the operating system. You have to develop drivers for many different operating systems, anywhere from Linux to Windows to Macs and whatnot. It's a slow process, and it's proven to be slow. But that's going to be one of the biggest drivers in changing landscape of memory computing. Think about this. For the last 70 years, we're relying on the fact that you can actually unplug the computer, plug it back, and you have a clean slate of RAM. This is no longer the case with volatile memory, non-volatile memory. You have to be able to adapt your software to really take advantage of that. That's not simple, by the way. I remember when, 5, 6 years ago, we looked at it the first time, we thought, well, it's kind of easy, right? We don't have to do persistent storage because we have a non-volatile RAM. It's not that simple. Actually, integration is pretty hard and non-trivial. And given the kind of glacier pace of this technology overall, it's going to be some process. But nonetheless, I do believe that you and I meet in 5, 10 years from now, that's going to be one of the major drivers behind the changes in memory computing. Almost every project in the memory computing space will be affected by this. But not only a new type of RAM, we have a new class of RAM. With the Intel Optane in the same way, we now have a spectrum of RAM. We have slow and cheap, and we have expensive and fast, right? You can have a DDR5 that's very fast but very expensive. You can have, something that is basically flash-based, like in Optane systems, where you can have terabytes of RAM, much slower RAM, but still a RAM, but addressable by operating system, on the system. So that's another interesting thing. Another advancement in the memory systems we're seeing is what's called interconnected RAM. So it's basically when you have a nodes in a rack, and in the connection between the nodes in a rack, so it's a very local, very much close connection, it's pretty much the same speed as your speed on the bus of your motherboard. So essentially, you can have a cluster of computers where the connection between them have no latency degradation between, whether it's internal components outside. So those things exist today. They're fairly expensive, but economics, will play the role and eventually will go down. So anyways, in the next 5 to 10 years, we're going to see a lot of development in this area, and the software will have to adapt to it. It's absolutely undeniable. Hybrid analytical transaction processing. It's a fancy word, and it's an interesting one. Essentially, if you look at this in the left side, that's what we do today, right? It's always fascinating when I ask, when I meet with the customers, and when there's opportunity comes around, I ask this question: why do you have separate analytical and transactional systems? Think about it. Why do we have that? Why do we have SQL, Oracle, MySQL, Postgres on one side, and then we have Hadoop, Teradata, or any other warehousing or analytics on the left side? Why do we have them separate? For what reason? They all deal with the same data. As a matter of fact, this duality creates this nonsense that we're constantly analyzing the old data. Because for us to analyze data, we have to first transition the data, basically ETL data, from transactional systems back to the analytical systems. Sometimes it takes days and weeks. Why do we have that? And essentially, the fundamental answer is that the performance. We don't want to degrade transactional performance with analytical queries. They use different technology. There's there is a common database on the left side. There is a raw database and then data grades in the memory computing on the right side. But fundamentally, it's all about performance. What we're noticing, and not only us, many analysts noticing, is that in memory computing is one of those enablement technologies that if you do it right, you can actually combine analytical and transactional processing in one system without significant or any degradation to your performance. That's a huge deal. Because if you could do that, that's billions of dollars of saving for a lot of companies. Think about, we have literally 2 mega industries that's completely bifurcated and separated, right? We have a transactional processing here, traditionally classical OLTP processing, and we have analytical processing on the other side. Those are hundreds of billions of dollars industries that exist only because we could never basically reconcile the performance of both type of systems. And then memory computing is one of those enablement technologies that over time will allow us to get closer and closer to kind of, a bit of a holy grail for the systems. We're actually seeing this today in our customers in GridGain systems where, our customers use our software to really, implement something like this today. We're obviously going to see it more and more as we go forward. Cloud native architectures. As I mentioned at the beginning, this is actually a fairly bizarre situation where, if you put aside the memcached implementation, elastic cache outside the brackets, there's not a single in-memory computing on the clouds. You go to Amazon or Google, go to anywhere, Azure, there's no in-memory computing platforms that are available as systems as a software as a service or as a platform as a service offering for any of the cloud providers. As a matter of fact, there's just recently, like in the last maybe 24 months, we started getting instances on Amazon with enough RAM to be interesting for memory computing. There's definitely a lagging factor for memory computing in the clouds, and that's going to be changing pretty rapidly. I've actually seen it changing, literally on a probably monthly basis, even from a GridGain perspective for our company. It's been you can explain it pretty easily. The current containerization technology and containers, they have a fairly significant degrading effect in performance. So for our customers, in-memory computing is all about speed and scale. So it's kind of contradicting. Why would you use something that actually degrades the speed and scale that you want to achieve in the first place? So it's not only about in-memory computing companies in the project. It's predominantly more about a cloud providers and container technology providers to really improve their game. But it is undeniable, and just by how many major tier 1 banks we've seen in the last 2 or 3 years switching 180 degree from not doing much on the cloud all the way to doing almost all the way to the cloud.
So this force is basically unstoppable, and cloud providers and memory computing vendors will have to adapt. And this is one of the biggest technological gaps that exist today, because in memory computing is a fairly complex beast. It's in the interaction with the memory system is very different from interaction with traditional databases. We don't have ODBC, DDBC drivers, for example. When you're dealing with a SQL database, it's a very simplistic view, right? Yeah, where, black box and the driver to it. It's a very easy to cloud enable to containerize it. Memory computing systems are different. We have a variety of different languages, from key value to SQL to NPP processing to all of this stuff that is hard to put in the cloud, hard to make a managed service offering out of it. And we're definitely going to be seeing this. This is one area where you're undeniably going to see a lot of advancement from every project that wants to stay alive and wants to stay viable and going to the future. Because this is the one, I believe, kind of last phase of a cloud adoption for a lot of high performance, ultra low latency applications and systems to move to the cloud. And memory computing is definitely one of those systems, or one of those type of applications. Last but not the least, and as I said in the beginning, this is one of my personal pet peeves. I always keep saying, nothing that is complex can ever get traction. Things that are complex, they don't go anywhere. They stay in this small kind of pool of enthusiasts and pioneers and never get traction as a technology. We've seen this with everything, right? We've seen this with Hadoop initially, and we've seen this with the memory computing. And memory computing is still perceived as one of the most complex software middleware ever existed. Think about this. Today, as I mentioned in the beginning, it's a combination of two complex and sophisticated concepts. It's storage and memory. It's a fundamental shift change in our thinking from a block-level device to the body-addressable RAM. Combine that, essentially, multiply that by distributed programming. That's what makes memory computing complex. You have to understand a very different type of storage and processing, and you have to understand intimately distributed programming and parallel processing. It sounds all pretty cool and exciting, but it bodes pretty bad for adoption. And one of the areas that we've seen us working in almost every other project in this area is to try to simplify the adoption, the learning curve, how quickly you can get effective with it. And it actually has a lot of, you don't have to rethink a lot. I think it's basically, you have to make many surgical cuts in many different places. Like, for example, we all got carried away many years ago with multiple versions of query languages. How many SQL dialects can we have that are totally incompatible? Well, why not use a normal SQL, adopt the normal SQL that we have? How many transaction paradigms do we have? It seems like every database that has a different transaction processing if you dig a little bit down under the hood. Why not have a normal transactions like traditional database would have had for many years? So it basically, it's a many different small changes that we should be seeing. And there's definitely a gap right now that we will be closing as a company and as a community in large, because there is significant demand for this. There is a demand for this easier adoption, to really break away from kind of top-tier engineers that can only basically use that, and I guess most of you here. We have to be able to used by a kind of more than middle-tier engineers in the larger groups. So this is an area that's basically, again, it's one of those 4 areas that will be driving a lot of engineering work, a lot of development in the product side for us and for many other companies. I know for a fact, as a matter of fact, when I say for many other companies, it's a small community. We know everybody. We know all our competitors. So we basically know what are the roadmaps for a lot of folks here. And when I say we, I truly know that it's we. Most of every other projects in this area and products and companies working on trying to simplify, trying to ease the adoption of the memory technologies. So, in the end of it, let's just summarize very quickly. I believe there are 4 areas that will drive a memory computing to even greater heights. And by the way, it's one of the most exciting technology already. This is basically what's powering up one of the key systems. Every name you guys heard about it in every financial institution, lots of companies in Silicon Valley. That's what basically under the hood for a lot of exciting projects today. New products in memory, new memory products That will be undeniably the most important factor from a hardware perspective that will drive adoption and change the memory computing. Support for HTAP and the cloud enablement are two areas that's also going to drive from a business perspective and a little bit more from a technology perspective. If you think about digital transformation that we're all going through, by the way, we're going to have another presentation after this about the cloud enablement, which will go much more in detail there. So support for HTAP and the cloud enablement is the two major kind of business drivers as well. And from a product perspective, and again, simplification is a key trend. And again, nothing that's complex can get traction. And in memory computing, we'll have to get simpler, we'll have to get easier to use. And I believe we'll work with 4 of these in the next 5 to 10 years. This will become one of the biggest trends in enterprise processing, data processing. With that, thank you very much.